You're listening to a podcast from the University of Manchester.
This episode was recorded during lockdown. Please forgive any issues with sound quality.
Hello and welcome to this episode of The Buzz. In this episode we speak to Dr. Aneeqa Khan and Dr. Laura Leay, nuclear researchers at the University of Manchester. We speak to them about all things nuclear. But first, I've got a fact for you, Joe. Do you know what links a boat called Lucky Dragon No. 5, Godzilla, and nuclear energy?
I have no idea.
Okay. It's a bit of a. It's a
I'm
bit
intrigued,
of a,
though.
Yeah, it's a bit of a long story, but I'll try to keep it short.
Yeah.
So, as you probably are aware, there was World War II ended with the nuclear bombs being dropped on Japan, and about 10 years or so later, there was some testing going on for the hydrogen bomb that America was developing, and basically the bomb was so big, it was like 3 or 4 times bigger than they thought it was going to be, and so when they dropped it, they kind of had a big exclusion zone, and they thought, we've got this zone marked off. If you're not in the zone, then you should be fine. The problem was, though, because it was so much bigger than they thought, there was a boat in the exclusion zone. And that boat's name was Lucky Dragon No. 5. It was this Japanese fishing boat. And so, unfortunately for them, it's a sad story. A lot of them got radiation poisoning and died of cancer and different radiation illnesses. But how it links to Godzilla is that about a month later after this explosion, the first Godzilla film came out, and so the film actually opens with a scene of this bomb going off, and because of this bomb exploding, Godzilla is kind of born, and there's also a boat at the beginning of the story, and so it's quite obvious that Godzilla is basically this idea. Godzilla is this manifestation of nuclear energy and nuclear bombs, and so often, public opinion on nuclear energy changes. We kind of look about that in this episode coming up. And so one of the ways you can kind of track public sentiment in Japan is by watching the Godzilla films. So there's so many Godzilla films, apparently. There's 36. I've only seen 3 or 4 of them. But each of the films, kind of Godzilla kind of slowly transforms. So from this, the first few films, he's this big scary monster. And so obviously in the wake of the nuclear explosions and stuff, people aren't big fans of nuclear energy, and so Godzilla's this horrible monster. And then as kind of Japan starts to develop nuclear energy and nuclear power stations, and public sentiment towards nuclear energy improves, Godzilla becomes this kind of friendly dragon guy who protects Japan from other monsters and other disasters. And so again, as public support grows, and nuclear public support for Godzilla increases. And so this again changes. So in 2011, you might be aware, there was the nuclear disaster at Fukuyama in Japan, where one of the reactors kind of went haywire, and a lot of nuclear waste was kind of released. And so again, the new film Godzilla in Japan, he goes back to being this scary big dragon guy and destroying the city. And so he's kind of come full circle, that Godzilla started off as this kind of warning against nuclear energy, gets good, and people love Godzilla. He's a big fan favorite in Japan, and then he becomes a monster again because of the nuclear disaster. And so, if you want to kind of chart public sentiment in Japan towards nuclear energy, you can kind of watch the Godzilla films, all 36 of them, and see that rise and changing attitude towards him.
Wow. So you said so. Have there been more since, after the recent one where he changed back to being the bad guy?
That is a good question. I don't know.
Because it'll be interesting to see moving forward whether the same thing happens again.
It would be. And obviously we have Godzilla in our culture as well now. It's not just isolated to Japan. We have, I think he's in one of the Marvel comic books at least, and I think he's a bad guy there. So be interesting to see if our culture also changes.
Yeah, definitely. Wow, really interesting. Well, I've got a fact. I don't think I can beat that one, to be honest. But did you know that the world's first nuclear reactor was created by the physicist Enrico Fermi? Now, any regular listeners to the podcast might recognise the name Fermi, as we discussed the Fermi paradox in the first episode of this season. That episode was when we asked the question, do aliens exist? So the Fermi paradox basically asks, where are alien life forms given the high likelihood that they should exist? But Fermi also works on the famous but very secretive at the time Manhattan Project, which was during the Second World War. And it was part of this project that the first nuclear reactor was created. And it was called the Chicago Pile 1, or it was otherwise known as the CP1. And it was first initiated on 2nd of December 1942. So around about 80 years ago, we've had nuclear power in some form. And Enrico Fermi is therefore often referred to as the architect of the nuclear age.
That's really cool.
Yeah, I found it interesting how he's stretched
everywhere
across these big ideas. Yeah,
definitely. I wonder if a future episode's going to feature him or not. Who knows?
yeah, it could be a thread running through the series.
Fermi Watch. Here we go.
Yeah.
Great, that's really interesting. We're going to find out some more interesting stuff now in this episode as we speak to Dr. Aneeqa Khan and Dr. Laura Leay all about nuclear energy. So first up, I know there's quite a big difference potentially around nuclear fission and nuclear fusion. So do you both want to kind of explain what nuclear fission is and then explain what nuclear fusion is and I guess any differences between the two?
Well, okay, so I work in fusion, which is basically what happens in the sun, and it's when you kind of join two atoms together. And Laura works in fission.
Yeah, so fission is the opposite, where you split some atoms apart to release a lot of energy. And I kind of sort of liken this to a really excited puppy. The atoms are already excited, or you can make them excited, and they're kind of like a really excited puppy running around losing all this energy. You can make a puppy excited by telling it it's going to go for a walk or giving it its favourite ball, and you can make atoms excited by giving them a little bit extra mass.
Okay, but you don't pull apart a puppy, right? That's where the analogy breaks down, thankfully. Great. So, which ones are we using at the moment? I've always heard that fusion we're not able to do right now. So is that true?
So yeah, we can do fusion, but we can't do it for as a commercial source of energy. So we can do it in labs and stuff, but at the moment we're having to put a lot of thermal energy in, and we don't get any electricity generated that goes in the grid from fusion reactions, and we don't have any commercial reactors. Fission, on the other hand, is pretty readily used in a lot of different places, and there's a lot of fission reactors where they split atoms and you can be generating electricity with fission.
Great. So Laura, do you want to kind of explain what a nuclear fission reactor, how it produces energy?
So I tend to work with nuclear waste, but I understand fairly well how a nuclear reactor works. So essentially, when your excited puppy or your atoms release their energy and they're surrounded by water, don't put a puppy in water though.
No.
So that energy heats up the water. The water boils and turns to steam, and that steam can be used to turn a turbine, and it's turning that turbine that generates the electricity by converting the kinetic energy from that motion into electricity. And there are a few different ways you can do this. You can have the cooling water from your reactor linked directly to where you generate your steam to turn the turbine, or you can have a secondary loop in there. So it can get really complicated, but the basics are essentially to boil water, which is what a lot of other types of electricity generation do as well.
That's great. And so you touched upon nuclear waste there as well. That's your research area. I guess, what is nuclear waste and why should we be concerned about it?
So I guess it's important to define exactly what you mean by nuclear waste. There is waste that comes off nuclear sites, but not all of it is radioactive. A good example is the mud that's coming off the Hinkley Point C, the new nuclear builds down south. That wasn't radioactive, which is why they could dispose of it in a fairly standard way, I believe. Some of the waste is radioactive, so we tend to refer to it more specifically as radioactive waste. There are different classifications depending on just how radioactive it is and how you may want to handle it as a result of its radioactivity. And it's things like it could be hand tools that a worker has been using that have become contaminated with radioactive material, or it could be the results of handling nuclear material itself. And whatever byproduct you have left over from handling it, say you've split it up into different chemical constituents, the bit that you don't want is classed as the waste, and that can be really radioactive. So that's handled in quite a very controlled way to make sure it doesn't release into the environment, so it's kept very safe.
I guess safety is a huge issue when it comes to nuclear. Are both these processes, fission and fusion, are they safe?
So yeah, fusion is pretty safe. The good thing about fusion is that you can't have a runaway reaction, because basically if the fusion reaction doesn't work, it just stops. It can't go crazy, I guess, which is the good thing about fusion. It's kind of difficult for us because it means it's hard for us to carry on the reaction long enough in order to generate electricity. So that's one of the things that people are working on at the moment, how you can keep the reaction going for a bit longer. But it's pretty safe.
Yeah, and with fission, there are so many different ways to design a nuclear reactor to make it safe. So we got the world's first commercial nuclear reactor in the UK in 1956, I think. So we've got an awful lot of experience in how to manage a nuclear reactor and how to build it in a way that it can be safe.
Great. And looking to the future, what are the main potentials of nuclear energy?
So from the fusion perspective, we really want to, generate electricity from fusion. It's still a little while away, but there's a lot of really exciting programs going on at the moment in order to make that reality. So we have the ITER project, which is in the south of France, which is like an international collaboration between EU, China, India, Japan, Korea, Russia, and the US. Okay, finally, I remember the 7 countries. But they're all working together basically to build the largest ever experimental fusion reactor and to, try and improve a lot of the technology that we will need in the future. So that won't produce electricity itself, but it'll prove a lot of the technology we will need to build commercial reactors in the future. So after that, the plan is to build a demonstration power reactor as part of the European pathway to fusion power. Other countries are also looking at other options. So the UK recently announced the STEP project, which is currently in its first tranche, and they want to build a prototype reactor, a spherical tokamak, which is a kind of special type of reactor, by 2040, I believe. So very ambitious. But going forward, there's a lot of other companies as well who are trying to develop different concepts for fusion reactors. So in the UK, we've got Tokamak Energy. You've also got General Fusion in Canada, who have quite a promising concept. And in the US, they've got the Spark reactor, which is a collaboration between MIT and Commonwealth Fusion Systems as well. So yeah, fusion is being explored in a lot of different avenues. So hopefully we will have commercial fusion power later this century, I hope.
Yeah, and UK government does have a remit to change the UK's energy mix, and the recent energy white paper still says that nuclear will be a part of that. So that would currently be nuclear fission, which of course we've got a lot of experience with, and there are new fission reactors currently being built. So energy generation will definitely be one of the future things for fission. And there are also a couple of other things that are being explored as well. So obviously I said you have water in your nuclear reactor. And when water is exposed to radiation, it can break apart and form oxygen and hydrogen gas. And hydrogen is being suggested as another way of getting energy. So we'd have a network of hydrogen distribution around the UK. So you could also use your energy reactor to generate hydrogen as well. And of course, you've got nuclear decay chain happening inside your reactor. So you start off with uranium, and that gradually over time changes into different chemical elements. So you could extract those elements and use them for other purposes. So a lot of electronics are beginning to have quite a lot of exotic elements in them to make them more efficient, or make them smaller, or make them do more things. So you could take some of those elements, the ones that end up being not radioactive, and using those to make new things. So lots of different things that current nuclear fission could be doing in the future.
Yeah, that's really cool, Laura, all the secondary applications with nuclear stuff. I read about desalination as well. It could be useful too, which is also quite exciting.
It sounds like there's lots of opportunities moving forward. What are some of the main challenges to nuclear energy?
So for fusion, I guess it's just building something that works. That's the main one. So we can do very like small scale reactors and stuff, but we've not managed to generate more energy than we're putting in to get the reaction going. So I guess that's the main challenge with fusion. More specifically within that, there's huge materials challenges, engineering challenges. Building the reactors is pretty complicated. So there's a lot of different concepts. What I work in is called magnetically confined fusion, which is exactly as it sounds. You use magnets to confine the fusion reaction. So the reaction that we want to use is between deuterium and tritium, which are isotopes of hydrogen. And essentially you bang those two together and you generate some high energy neutrons and some helium, and it's you get a lot of heat, but containing that reaction is pretty challenging. You get something called a plasma, which is when you really heat these ions to extreme high temperatures. It's like the fourth state of matter, kind of like a rod of lightning, and you use magnets to hold this all in a donut shaped device called a tokamak. But building one of those is really hard because you need materials that can withstand those really high temperatures. So in like the center of the plasma, it's something like 10 times hotter than the center of the sun. It's like 150 million degrees.
Wow.
Yeah. At the walls of the device, it's not as hot, but it still gets pretty hot. So having materials that can cope with those high heat loads, with the high energy neutrons, with the helium gas, with the high magnetic fields. So I think in ITER, you're getting magnetic fields of like 13 Tesla. And if you compare that to like a PET scan in a hospital, which is like 1.5 Tesla, really high magnetic fields. So generating those magnetic fields is also a huge challenge. And there's different concepts being explored for those generating those magnetic fields as well. So a lot of big materials and engineering challenges.
I guess the reason that we're addressing these challenges is because you can get an awful lot of electricity generated from a small amount of material, so it would eventually become more efficient. And obviously there isn't any CO2 produced because you're not burning coal or gas or anything else, so those challenges are worth trying to address. In fission, I guess I think there's a bit of a legacy that most people seem to think that it's quite dangerous, but don't necessarily know a lot about what actually goes on in a nuclear reactor or what we do with the waste, because the nuclear industry hasn't really talked about it a lot in the past. So I think one of the big challenges is about getting people to understand what can be quite a technologically complicated technology, and making it more meaningful to them so they can see how it works and how it's beneficial. There's also, it's a highly regulated industry because there are safety concerns to think about. So the regulations do tend to slow things down. People want to be really, really sure that we're doing the very best thing that we can possibly do. So there's a lot of discussion by a lot of experts around the world about what that looks like. And that all takes time. So it can take quite a long time for any new technology in nuclear to be realised. And that makes it expensive in a way, because you have to think about these regulatory challenges.
Yeah, I was looking into why we don't have a lot of fission, at least in the UK and around the world. I know France do have a lot of their grid is done by nuclear energy. Do you think it is just one of the reasons is that stigma around nuclear energy and kind of thoughts around kind of nuclear weapons and nuclear disasters like Chernobyl? Do you think that plays a part, or is there something more going on?
I've not seen anything that leads me to believe that it's anything other than this perception that we have to be really, really careful, and we have to make sure everything is absolutely safe before we can do anything. The industry is generally considered to be risk averse, so it doesn't like taking risks, which is a very sensible approach, but it does make things quite slow. So yeah, I'm not aware of anything other than this challenge of risk.
And the thing with fusion as well is that we don't have any we have regulations, but it's not an industry yet. So it's not, the nuclear industry the regulation is all based on fission, but the challenges in fusion are so completely different that I think going forward, and it's something that needs to be worked on now, basically, is that when we do prove all the technical challenges and get everything up and running, we need to have that regulation in place as well. And it will look quite different to the regulation for fission, I'm guessing, because the challenges are quite different.
Yeah, I imagine so. I wonder if one commonality could be perception of risk, which is quite a big thing. For example, like people think that nuclear is really unsafe but don't know why, but then crossing the road, if it's busy roads, is really unsafe as well. So there's that perception of that thing that we recognise and we know we think is safer than that thing that we don't know. So again, it's all about the perception rather than, I guess, what the experts know to be true but haven't necessarily communicated all that well, possibly because they know it so well that it's a challenge to communicate something that you already understand quite well, if that makes sense.
Yeah, definitely.
Yeah, I've heard that even like fossil fuel energy production actually also people die because of that, either in terms of mining the material or kind of just the atmospheric changes because of that. And so it's not as if there aren't dangers of using these other ones. And so I guess it's kind of, promoting the benefits of nuclear being a cleaner energy as well as a fairly safe energy in terms of, these accidents happening very rarely, and we have better and better controls to prevent them from happening in the future.
Yeah, that's very true. You often only hear about something because there's a big sensational event, like an explosion or a plane crashing if it's aerospace. But aerospace air travel has been demonstrated to actually be safer than driving in a car because of the frequency of accidents. And there are also other less direct effects, like burning coal deteriorates air quality. So that has an effect on, like I said, people that have asthma. It makes them more sensitive. So the indirect consequences of what you're doing could be taken into account as well. Burning coal also releases more radioactivity into the atmosphere than nuclear power does, because nuclear power contains all of its waste, whereas coal burning just releases all this stuff into the atmosphere. So there are all these quite interesting interplays to consider that I think people just often think, oh, nuclear is unsafe, everything else is safer in comparison.
Yeah, I guess then what are your hopes for the next kind of 20, 30, 50 years or so? Do you hope that we do have a lot more, I guess, both fission and potentially, who knows, fusion reactors running in the UK and around the world that are providing energy? Or is there any other kind of applications of nuclear energy that you can see happening in the next, half a century or so?
Yeah, absolutely. I think it'd be great if we could have more nuclear reactors. And as Laura mentioned before, all the secondary applications, I think they have a huge role to play. So stuff like to do with the hydrogen economy, which Laura was mentioning, I think that's going to be a big thing moving forward. And yeah, from my side, having fusion reactors up and running and potentially delivering electricity, optimistically, maybe 50 years away. I know people always say that about fusion, but that would be amazing. But yeah, definitely need more nuclear.
I think I think we've talked quite a lot about the benefits of nuclear, so clean electricity generation and transmutation of elements and things like that, and hydrogen economy. I think there's also something there about public communication of science. I feel like certainly when I was a child, anyone that was interested in science was classed as a bit of a geek, and therefore not a person that would be seen as a very appealing person to talk to. Whereas I was talking to some mates that work in robotics a few years ago, and like, hang on, loads of people are really interested in what we're doing. I'm like, yeah, we're the cool kids now. But there's still this idea that, science is really complicated and it's really difficult and I can't possibly understand it. And I think you can. It's just finding the right way to communicate these things that resonate with the person that you're talking to. So I think that's the challenge for the industry. and something I'd really like to see more of in future, to have the industry having this really clear dialogue with people that really resonates with them.
Yeah, I think that's a really good point, actually, Laura, communicating things really well. And I think starting with like kids as well at an early age in school and stuff, and getting them interested. Like, so for me, when I was in school, I was actually really against nuclear energy, just from the way that it was like portrayed in the media and stuff like that. But then obviously when you learn about it and get educated, and you see how important it is, especially if we need to meet, reduce our carbon emissions and try and tackle climate change, it has got to play a role in that. So yeah, I think communicating this really clearly is so important.
Yeah, and I think sometimes that can be a challenge, because you only really see things in the news when they've gone wrong. Like, as I said, a plane crash or an explosion. You often don't really hear about the really positive things that something can do. So maybe there's some sort of rebalancing of things the media portrays as well.
The what was it called? Discoverer drone, not drone, satellite thing that went into space. I heard that was nuclear powered. That it was on this kind of, but in my head it's tiny. So how can it have a nuclear output?
Space batteries, isn't it? Aneeqa, are you aware of this?
I'm googling it as
Yeah, space batteries are definitely a thing, and they are nuclear powered, but it's a very different kind of power to having like boiling water or the fusion that Aneeqa works with. So what they do is they take something that's radioactive. It doesn't necessarily have to be uranium like you'd find in a fission reactor, but it gives off energy as it undergoes radioactive decay, right? And if you put something on very close to that source, it will absorb the energy, so it'll absorb it as heat. And you can use that heat to generate an electric current depending on the composition of your device. I think it uses semiconductor technology. So you apply some heat to it, that generates a current, and then you can use that to power your electronic devices. I don't think it's a particularly high current, although I could be wrong. So they still think quite carefully about the power systems on their devices. But yeah, it's a very viable technology.
Wow,
that's really cool. Because I know again, this is more than 50 years in the future. I'm sure, like the idea of like cross galaxy travel or cross, outside of the solar system travel could be nuclear reactors that we are able to kind of harness in spaceships and stuff is always the pipe dream of nuclear.
I think there's a company looking at this as well. I think Princeton Satellite Systems, because I feel they're giving a talk at the university like early next year, and I think theirs is something to do with like, nuclear fusion powered propulsion.
Sounds like it could be a good opportunity for better, more positive communication about nuclear energy, like we were speaking about before.
Yeah, definitely. Just seeing the different applications for it, I think it's really exciting.
Yeah, and I guess the other kind of question I had was around kind of nuclear power plants and kind of if we have to be like, I feel like one of the big barriers to building them in the UK at least is like people don't want it near them in case something goes wrong, right? So that's why we have offshore ones, or we have ones in the middle of like kind of right on the coast or in the middle of nowhere. And so I guess like, do you see that as a problem persisting in the future, or do you think people will become more accepting of nuclear power stations near their house?
I think, as Laura was talking about, it's all about the communication and this like sharing the social value of the nuclear reactors with local communities and stuff is really important. And actually, I remember reading some research in areas where there are like nuclear reactors. So like Laura's in Cumbria. I think there's a really good public perception of nuclear power in Cumbria, if I'm not mistaken. Laura, is that correct? Or
yeah, that's exactly right. I mean, so Sellafields used to generate power, and then it went into reprocessing, and now it's undergoing very long timescale decommissioning. But it's a really big employer in Cumbria. And it's not just that it gives people jobs, it also gives people opportunities. You have there are so many interesting technical challenges. So it's a great way of getting people to learn about something that's really complicated and do it in a really hands-on way. So I think the people that actually live right next to Sellafield, I guess you could class me as one of them. I live about 9 miles from the site. We see it as quite a good thing. And I think people are quite accepting of the risks as well, and recognise probably more so than some other people what those risks are. What our perception of it is probably less so than someone that doesn't know as much about the area. So yeah, I think you're right. People are more accepting of nuclear around here, but they get to see it more. They get to realise the benefits, and they get to understand how it works in more detail.
Sure. I guess with you living so close, have you ever had like a talk at class at school or anything about what would you have to do if an alarm goes off and there's nuclear contamination?
I haven't. I know that there are regular exercises on the site to understand what we'd do in the event of something like that. And it's all been happening for so many years that the site is so used to doing these things, and the people around here are so accepting of it that there isn't so much of a need to perform classes like that, as far as I'm aware.
I remember I went to Chernobyl last year. Oh, this year has been long, hasn't it? I went last year, and that was just really interesting. Like I came away with it not being like anti-nuclear as I thought I would, like being actually quite pro-nuclear in terms of like this happened, but we now have better safeguards, and we now have we can use that tragedy as a kind of almost like spurring us on to do better with nuclear. I wasn't like put off nuclear energy because of that, which I was quite surprised by actually.
No, I find it interesting that the two companies are sort of they're taking this opportunity to show people what it is and generate a business out of it. We went to Chernobyl a few years ago when the Beast from the East was happening. We got stuck in the snow in the exclusion zone and had to push our bus.
No. Had to push the bus.
Yeah, we were the only people there in this like massive coach. All the other tourists were in these smaller sort of like 16-seat minibuses. We were having to help them out as well. It was just really weird, like international cooperation, because we didn't necessarily speak their language, didn't necessarily speak a lot of English, so we were just sort of like communicating through hand gestures and just like all pitching in to help each other out. It's very, very strange.
It does sound very strange.
Oh God.
Yeah, so you probably got to see more of Chernobyl than we did.
Possibly, yeah. I guess we also just wanted to ask about your own research. What are you doing, and what are you researching in nuclear?
I don't know like how much detail to go in, because I could talk for hours. But yeah, basically, I do research in materials and engineering for fusion applications. So as I mentioned before, you have a plasma in your fusion reactor, and that will interact with the materials on the walls. So I'm really interested in that plasma material interaction, how it changes the properties of the materials, how we can join materials, because a lot of the time you need different materials in different places, and joining dissimilar materials is really challenging. So we're looking at like different types of welds we can use to join those materials, and you have to make quite complex shapes. As I mentioned, the reactor's donut shaped, and the shaping is kind of very complicated. So manufacturing and joining components and making sure that they can cope with the extreme conditions is what I'm interested in.
So how do you even test that? Like, do you have plasma in your lab, or do you kind of do computer models of this?
So it's a huge international effort in this. So the best way, I guess, would be to put everything in a fusion reactor, because you need to look at the combined effects. So you need to look at the high temperatures, the plasma, the neutron effects. But as I mentioned before, the neutrons have a very high energy, 14 MeV. And we don't have a 14 MeV neutron source, so we have to use other techniques to kind of mimic that damage we'd get from those neutrons. So Manchester actually has a ion irradiation facility up in Cumbria, Dalton, Cumbria facility, where you can bombard materials with either ions or with protons, and that mimics the neutron damage. And then we analyze that using a variety of techniques, such as electron microscopy or other kind of micromechanical testing, because the samples are really small. That's the big challenge with a lot of the work we do. We can only look at really small samples, but we need to extrapolate that to a large scale. So that's a big challenge. So often people have to use a combination of modelling and experimental techniques to look at that. And then there's a lot of other like facilities around the world which have like plasmas. So there's these things called linear plasma devices, which essentially just shoot a line of plasma at your material as well. And it's the same thing. So you expose your materials to plasma and then you do the analysis in the labs to kind of see how their material properties change. But it's a really collaborative kind of work because we have to work with a lot of different labs and places who have these different techniques that we can use to damage our materials, and then we do the analysis here to see what's going on. One thing that's really interesting at the moment that I don't work on in fusion, and is also very, I think, relevant in the times of Corona when it's often quite difficult to get into labs and stuff, is in silico modeling, which is essentially just making like digital versions of your experiment as well. So trying to recreate experiments digitally so you can kind of narrow down the materials that you would eventually investigate with experimental techniques as well. It is a pretty cool area of research that's going on at the moment.
And Laura, you do nuclear waste. What do you look at specifically?
So my research group is based at the Dalton Cumbrian facility. So what we're interested in is how the nuclear waste or the radioactive waste's own radiation field will affect the waste over time. So Aneeqa already mentioned we have a particle accelerator system that can deliver some really high energy particles to different materials. We also have a gamma irradiator. It's completely shielded, so it's basically operated like a big microwave. You put your sample in there and it's exposed to gamma rays, which are a different type of radiations. They have different effects. And so we've got all this different suite of devices that we can use to apply radiation to our materials, and then we look at what sort of changes happen as a result. So we see things like ions moving around in glass. So one of the ways of treating nuclear waste is to incorporate it into glass, turns it from a liquid into a solid. And you also drive off a lot of the liquid as well. So you reduce the waste volume, and being solid, it makes it easier to handle. Glass is an amorphous material, so it doesn't have any long-range order in its atoms, which means it's quite good for incorporating nuclear waste because radioactivity tends to make things amorphous. So if you have something that's really crystalline, like a diamond, say, it will move those atoms around until they're less regular or less crystalline. So glass is pretty good for incorporating the waste because it's quite radiation tolerant. There's quite a lot more going on at that atomic scale. So I said you've got ions moving around. You want to make sure that all the different chemical elements within the waste aren't going to come out of the glass, and radiation can have an effect on that. So that's one other thing we look at. And we also look at cementitious materials as well. Cements are quite useful for encapsulating waste, so wrapping around it essentially. So you can take lots of small pieces of waste and turn them into a big block. Cement is made with water, so you can break down the water with the radiation. So we want to understand just how much breakdown will occur, and then what will happen to the gas that's generated as a result. We also want to know that that big solid block will still be a big solid block in many decades of time when the waste is disposed of underground.
Yeah, so in my head, nuclear waste is this green glowing liquid, but in these big canisters with a nuclear symbol on, and then that's buried somewhere in the earth. I assume it's more complicated than that, but you mentioned about burying it underground. Is that what we do generally with the leftover waste?
That is the intention. There's been an awful lot of research in this area by the international community, and putting it underground is deemed to be the best method. So it puts an awful lot of material between us and the waste. But I guess the media commonly portrays this as dumping the waste. But what we'd actually do is produce a highly engineered store. So it would have all these barriers between the waste and the environment. And the waste itself is packaged in such a way that it will remain safely sitting there. It's called passive safety for quite a while anyway. So we're putting in all these layers of safety to make sure that when the waste is put underground, it will still remain safely locked away from us for, I think we're saying hundreds of thousands of years. It's quite a long time.
Yeah.
So it's quite a challenge to predict how the waste will change over that intervening timescale.
Yeah. And then I guess just finally, if someone's listening to this podcast and they want to find out more about nuclear energy, have you got any idea of resources they can access or any websites they can go to find out more?
So the Dalton website has a load of nuclear resources that are really useful. So I recommend people check out the Dalton website.
Yeah, and the International Atomic Energy Agency has loads and loads of educational resources as well. So I guess probably the best way to find out about a particular thing would just be to type it into Google and see what it comes up with on the IAEA website.
And for fusion stuff specifically, the ITER website has a load of resources on there that are really useful.
Yeah, and another really cool resource, EDF have generated it's an online game you can play where you have to sort of supply enough energy to meet a demand of a country. So you have a little map of towns with lights that light up, and you have to try and get enough lights to light up to make people happy to keep the lights on, as it were. And you've got different energy mixes you can use to do that, so you can see the effect of having like all wind versus all solar versus all coal or all nuclear or some combination of those technologies. So that's pretty interesting to get your head around why the government have decided on a particular energy mix.
A huge thank you to both Laura and Aneeqa. Make sure to check out some of the resources they mentioned at the end of the episode. Next time on The Buzz, we're going to be looking at robots. More specifically, we'll be looking at robots that have been inspired by animals. Be sure to check it out. If you have any comments or questions on today's episode, you can email us at fsemarketing@manchester.ac.uk. You can also find us on Twitter and Instagram, where we are at UOM-SciEng. You can also find us on Facebook, and you can even find The Buzz on YouTube. Thanks for listening, and see you next time.